Hello. Now that you have some fundamental understanding of the vibration of particles, now do you have some fundamental understanding of the vibration of particles? You are familiar with this vibration. Now, in nature, these kind of simple harmonic vibrations are rampant. In fact, energy transferred from one place to another. How do we transfer energy from one place to another? It is actually one very, very popular way of doing that is by setting particles into vibration. Now, I want you to watch this simple illustration I have set up for you. Now, here I have constructed a medium. Now, what is this medium? I have a tape, and on which I have stuck some very light straws. Now, if I can set one of them into vibration, all right, I want you to watch and think about it carefully. If I give it a little jerk on this one, this will vibrate up and down, and because each of these is connected by means of the tape, the energy of vibration will get handed over from particle to particle. I'm going to call each of them a particle. Now watch carefully how they vibrate if I set the first one into vibration. Now, there you are. Do they all vibrate at the same time? No. Now what's the difference there? If this one starts vibrating, the next one starts vibrating a little later. The energy gets to each of these particles a little later, and as a result, each will vibrate. I'm going to develop this word, you've got to understand that. Each will vibrate in a different phase. Now look at that. Each will vibrate in a different phase. Another illustration of energy transfer through a medium. I have now here a stretched spring. I suppose you can see that. Each segment of a spring is actually a particle. I can set one particle into vibration. Tell me what happens if I pluck, I'm going to pluck this upward and leave it. Watch what happens. Can you watch what is happening? The energy that I used to pluck it up and down, transferred all the way to the other end of the spring, gets back and forth. The energy travels through the medium, and you can see it takes time for each particle to get energy from the nearest particle. This brings us to an important phenomenon in nature called wave motion. What is wave motion? Well, let's look at a couple more examples. If you tie one end of a rope to a support, stretch it by pulling it on the free end, and give it a sudden jerk upward, well, just like I did it on the spring. Now this is what will happen. The sudden jerk will set the particles of the rope into up and down vibration, and that energy of vibration gets handed over from segment to segment until it reaches the other end of the rope. Then that energy gets reflected back. Now, this is another illustration of the same phenomenon. You can see a pulse that I generate here. The pulse will move gradually to the right. Well, it happens actually very quickly because the energy, the elastic force binding the particles together are very strong. So you see a pulse moving along the rope. When the pulse reaches the support, it gets reflected back, and you can see how energy travels back and forth through the medium of the spring or through the medium of the rope. So the jerk, the energy of the jerk set the segments into simple harmonic vibration, up and down vibration, and the energy of vibration gets handed over from particle to particle. The energy of the jerk gets passed on from segment to segment due to the elastic properties of the string. You see that? It's the elastic properties that binds the particles together. Now, remember, the rope segments do not move away from their positions. The rope segments simply vibrate up and down like this particle. You see that? Each segment executes simple harmonic vibrations just like the simple harmonic vibrations of the spring, and the energy gets transferred along the medium. Okay, the energy of vibration travels along the length of the rope. Each segment of the rope is set into vibration a little later than the previous segment. Do you understand why each segment starts vibrating a little later than the previous one? That is an important concept. All right. Now, you can see here the vibration of the spring, and if you create waves in water, have you actually seen how waves in water can be created? If you drop a pebble into a pool of water, you can see the water will keep moving up and down, and that up and down motion of each water particle is transferred from particle to particle. The energy transfers, energy travels along the surface. You can see if you keep an object like this on the surface of water, you can actually see that object does not move away. That object will simply move up and down in simple harmonic motion. Try it next time. Take water in a wide container and drop a pebble into it, and keep a small piece of paper at some point on the surface. You can see that paper will simply move up and down. The energy will go past it, but the water particles are not moving away from their positions. It's very important to understand that. Alright, so when a pebble is dropped into a pond of water, the pebble sets the molecules of water into simple harmonic motion, SHM, just as the oscillations of this loaded spring. As the energy reaches each molecule a little later, you can see the wave profile is created because the energy reaches each particle a little later. When a particle here has vibrated all the way up, a particle here will just begin to vibrate. You see the profile of the wave. We will create the profile as we go on. Each subsequent molecule will be in a slightly different phase of vibration. I want you to understand this. I will develop this in our next couple of slides. Now, it is this progressive phase difference. If you move from particle to particle in a medium, there will be a progressive phase difference. And it is that progressive phase difference that creates that wave profile. So, if you understood anything what I have said so far, we can use all that concept to define wave motion. What is the definition for wave motion? We can say wave motion is a kind of energy transfer in a medium. The medium may be water, it may be the straws with the tape, it may be the spring, it may be air, you see? So energy transfer in a medium due to the vibrations of the particles of the medium, with the particles themselves, without the particles themselves moving away. You see, each particle will simply vibrate up and down. This particle will not move away from its positions. It will stay in its equilibrium position. The particles themselves do not move away from their respective positions. Alright, now let me see if I can show an illustration to you. Now here you have an example of a medium. I have constructed a medium here by lining up some students. You can see if they are holding hands, one goes up and down. Look at how the energy of vibration get transferred from one. I'm going to call each student a particle. The first particle begins to vibrate, the second particle begins a little later, and look at the profile gets generated. Now this is called a wave profile. Now what is the profile due to? The profile is due to the fact that there is a progressive phase difference between particles in vibration. Alright, I think we have been using this word phase difference quite a lot. Let's now try to understand the meaning of that. Let's now try and understand the meaning of phase of vibration and phase difference. Now here I have a particle, my basketball. If I set it into vibration, I want you to watch some of the terms I'm using. If this is the equilibrium position, it vibrates to an upper extreme. You can see that is the phase of vibration now. Back to the equilibrium, to the lower extreme, back to the equilibrium. That's one vibration. You see, each phase of vibration, the particle is at different positions. Alright, so what is the meaning of phase of vibration? Let's consider several particles oscillating between two extremes. Now here I have particles 1 and 2. Particles 1 and 2 are at the equilibrium position and they are both moving up. Now let me see if I can illustrate that here. If I have particle 1 and particle 2, they are both moving up together, back to the equilibrium, down, back to the equilibrium. We can say they are both in the same phase of vibration. So particles 1 and 2 are in the same phase of vibration because they will be always at the same positions. You see, they are in step. They are both in the same phase. There is no phase difference between them. When particle 1 is at the upper extreme, particle 2 also is the upper extreme. Particle 1 is in the equilibrium position, particle 2 is also there. There is no phase difference. While particle 3, watch the motion of particles 3 and 4. While particle 3 is beginning to move up, particle 4 has completed going up and coming back to the equilibrium position. It is now beginning to move down. Alright? I want you to understand that the phase of vibration is associated with the position. Look at this. Equilibrium position, upper extreme, equilibrium, lower extreme, back to the equilibrium. Now, remember, the time taken to vibrate completely once is called a period. Now look at these two particles now. Now, particle 2 has gone to the upper extreme, back to the equilibrium position, and now it is beginning to move down. And particle 1 is beginning to move up. Now that means this particle in my right hand. Now when I say my right hand, it will look like the left hand to you in the picture. You see, this particle that is beginning to move down is half a period ahead of the particle that is moving up. Now what does that mean? Remember, the time taken to go up, back and down and back is one period. So this particle has gone up and come back. That means it has already covered half a period. So we can say particle 4 is half a period ahead of particle 3. When particle 3 begins to move up, particle 4 has completed half the vibration and begins to move down. I hope you got a picture of what that is. Particle 3 has to go to the upper extreme and back to catch up with particle 4. So by the time 4 would have gone down and back, they are always moving in opposite directions. Now, what is the phase difference between particles 3 and 4? You can actually, we define phase and phase difference using the angle. Now, I want you to understand the angle concept. All right, give me a second. I will review that with you. The angle as the particle begins to move up. Remember, when it is all the way up, the angle is pi by 2 and the period is t by 4. When the particle is back at the equilibrium position, the angle is pi and the period, the time, is half of the period. When the particle goes all the way down, the angle is 3 pi by 2, you see? And what is the time in terms of the period? It is 3t over 2. And finally, when the particle is back at the equilibrium position, the angle is 2 pi and it has completed one period. Alright, I think I made more of a mess here than explaining, is that right? Now, let me try it once again. Now, if the particle is at the equilibrium, we say the angle is 0, the period t, because it hasn't started, is 0. In a quarter of a period, it reaches the upper extreme. Then the phase angle is pi by 2. In half of the period, when the period is half of the period, the phase angle becomes pi. You see that? In 3, when the particle goes down to the lower extreme, it has now completed 3/4 of a vibration. So the phase is 3t over 4, which is the same as 3 pi by 2. And when it is back to the equilibrium position, one full period is the same as the phase angle of 2 pi. So the phase difference between particles 3 and 4 is pi, because particle 4 is half a period ahead of particle 3. Alright, can you now tell me, looking at this, what is the phase difference between particles 5 and 6? 6 has just completed quarter of a vibration. The phase difference is a quarter of a period, which is the same as pi by 2, a phase angle of pi by 2. Alright, so tell me, what is the phase difference between particles 7 and 8? Particle 8 has completed what part of the vibration? It has completed 3/4 of the vibration. It is now left only the last quarter. That means its phase is 3t by 4. Is that right? 3t by 4, which is the same as 3 pi by 2. The phase difference between the two is 3 pi by 2 phase angle. In terms of the period, it will be 3t by 4. Alright, now here I have how many particles? 5 particles of a medium. Consider 5 particles of a medium oscillating with a phase difference of t by 4. What does that mean? What is the meaning that the phase difference is t by 4? It means when the first particle completes quarter of a vibration, the energy will just reach the second particle, it will begin. That is the meaning there. And when the energy reaches the third particle, the second particle would have completed quarter of a vibration. The first particle would have completed half a vibration. Alright, let's set it up like this. If the phase difference between successive particles is t by 4, remember that t by 4 means quarter of a period. As the first particle completes 1/4 of a vibration. 1/4 of a vibration means from equilibrium it will go all the way to the upper extreme. There you are. So particle 1 has now completed 1/4 of a vibration. It is now at the upper extreme. The energy will now just reach the second particle. Now look at the profile of these two particles. They are not in the same positions anymore. After another quarter of a vibration, after another quarter means after half a period. You see, this is 1/4. After another quarter, the energy is going to reach this particle. So tell me, where is the first particle now? The first particle has completed one vibration. Completed half a vibration. You see that? The second particle has done a quarter of a vibration, and the energy just reaches the third particle. And look at the profile of the three particles now. Alright, what happens after another quarter of a vibration? Now how many quarters? It is now 3/4 of a vibration. So the first particle has now completed 3/4 of a vibration. Where is it now? It is at the lower extreme. Where is the second particle? It has completed half a vibration. It is at the equilibrium position. There you are. Now where is the third particle? It has completed quarter of a vibration there. And the energy reaches the fourth particle here. And look at the profile now. Isn't that beautiful how the wave profile takes shape? What is the situation after another quarter of a period? After another quarter, particle 1 has completed one vibration. That is one period. Alright? Particle 1 has completed one vibration. Where is particle 2? It has completed 3/4 of a vibration. It is down here. Where is particle 3? It has completed half a vibration, back to the equilibrium position. Particle 4 has completed a quarter of a vibration, and the energy just reaches the fifth particle here. And look at the wave profile. And now, can you tell me, what is the state of vibrations of particles 1 and 5? Particle 1 has completed one vibration, is now ready to start the next vibration. And particle 5 has just received the energy, it is ready to start vibration. Is that right? Yes, that means particle 1 and particle 5 are going to be now in the same phase of vibration. Right? Particle 1 and particle 5 now begins to move up at the same time. That means they are in the same phase of vibration. There is no phase difference between these two particles. You can see the meaning of a progressive phase difference that creates the positions of the particles at the differences of the position that creates the wave profile. By the time particle 1 completes one vibration, look at the energy has reached the fifth particle. You see? Very important information. The distance advanced by the wave in a time of one period. You see? The time taken by the first particle to complete one vibration is one period. And what is the distance advanced by the energy during that time? Is the distance between particles 1 and 5. Now, this distance is called the wavelength of the wave. So tell me, what is the definition of wavelength? An important concept. Wavelength of the wave is the distance advanced by the wave in a time of one period. That is the definition of wavelength. Wavelength is represented by the Greek letter lambda. Lambda. Alright? So this length is the wavelength. Wavelength is represented by lambda. The distance between two nearest particles that are in the same phase of vibration is wavelength. Another definition, or the basic definition of wavelength, is the distance advanced by the wave during a time of one period is wavelength. So, wavelength can also be defined as the distance between two nearest particles in the same phase of vibration. Alright, now that is the concept. Let's take a look at this particle. This particle is going to vibrate up and down, and the distance advanced by the energy or the wave during that time will be a wavelength. Now take a look at it when I run it. Now you can see the particle vibrates down, back to the equilibrium, up, back to the equilibrium. One complete vibration. The distance advanced by the wave is a wavelength. Now look at the profile of the wave. We say a wave has a crest and a trough. Now here, the particle here is at the upper extreme. The particle here is at the lower extreme. And that is the difference between the crest and the trough. Okay. Let's now obtain an equation to represent a wave. Well, the equation is going to be using the definition of the wavelength. We can now use the definition of the wavelength to get an all-important equation of the wave using the wave speed. Now, if v is the speed of the wave, how do you define speed? Speed is distance divided by time. Is that right? So speed v is distance traveled divided by time. Now just look at this. If this is the distance traveled, tell me what is the time taken for this distance? The wave advanced by this distance in what time? In one period. So, if this time is one period, then this distance will be one wavelength. Is that right? The wave travels a distance of one wavelength represented by lambda in a time of one period. So, in this equation, if I replace the time by one period, this distance then becomes the wavelength lambda. So, we can say v, the wave speed, equal to wavelength divided by the period. You see how we obtained the wave equation. And now, look at the way I wrote it. Lambda divided by t is the same as 1 over t multiplied by lambda. Now, why did I write that way? Can you give me a quantity that is equal to 1 over the period? 1 over the period is the frequency. Is that right? Reciprocal of the period is the frequency. So 1 over t equal to f, the frequency. Therefore, this is the all-important wave equation. Wave speed equal to wave frequency multiplied by the wavelength. V equal to f lambda. Now, this is true for all kinds of waves. The waves that we talk about in this lesson are mechanical waves. Waves that are generated in a medium by the vibration of the particles. This equation is also true for electromagnetic waves. See, light is an